Hi, I'm Faraz Torabi, a PhD candidate at the University of Texas at Austin, and I'm going to be presenting RIDM, Reinforced Inverse Dynamics Modeling for Learning from a Single Observed Demonstration. This work has been done in collaboration with Brahma Pause, Josiah Hanna, Garrett Warnell, and Peter Stone. The motivation of this work is to allow an artificial intelligent agent to learn tasks when a demonstration is available, a reward function is available, the demonstrator is suboptimal, demonstrator actions are not available, not many demonstration trajectories are available, and only raw state information is available. So first, I'm going to give some background. The first framework that I'm going to talk about is reinforcement learning. The goal of this framework is to learn how to make decisions by maximizing the cumulative reward feedback. This is how this framework works. There is an agent inside an environment. Let's say it's in state ST, and it takes action AT, and it goes to next state ST plus 1. During this process, it gets a reward feedback RT plus 1. And the agent tries to maximize the cumulative reward feedback to learn the task. The next framework that I'm going to talk about is imitation learning. The goal of this framework is to learn how to make decisions by trying to imitate another agent. In this framework, observations of other agents consist of state action pairs. The inclusion of action inside the demonstration results in a limitation. It precludes using a large amount of demonstration data where action sequences are not given. So here is an example of imitation learning from Scott Nicholm, where he tries to show the robot how to draw a cross on a whiteboard. And here the agent, which is the robot, has access to both the states, which are the joint angles, and the actions, which are the joint torques. The next framework is imitation learning from observation. The goal of this framework is to learn how to perform a task given a state-only demonstration. This framework is very natural to humans and animals. They watch others doing tasks and they try them themselves and learn tasks. The formulation of this framework is that we are given a state demonstration, a state trajectory, and we want to learn a policy which maps states to actions. So now I'm going to give some related work for each of the frameworks that I just talked about and their intersections. I'm not going to go through the details of these papers. These are just for the reference, and if anyone was interested, they can look them up. So there has been some work in reinforcement learning, in imitation learning, in their intersection, and in imitation learning from observation. However, our paper is the first paper in the intersection of imitation learning from observation and reinforcement learning. So our goal is to combine imitation learning from observation and reinforcement learning to learn tasks when, as I stated at the beginning of the presentation, the demonstrator is suboptimal, demonstrator actions are not available, not many demonstration trajectories are available, and only raw state information is available. So in this formulation, we are given a single state only demonstration, which could be suboptimal, and a reward function. And we want to learn a policy to perform the task. So now I'm going to talk about our algorithm, which is RIDM, Reinforced Inverse Dynamics Model. So RIDM represents a new paradigm for combining imitation learning and reinforcement learning, in that the agent's behavior is driven directly by the fixed demonstration trajectory coupled with a parameterized inverse dynamics model. In RIDM, demonstration is treated as fixed, and the reinforcement learning is to select the inverse dynamics model that causes attempting to follow the demonstration to lead to the highest environmental reward. That is, the system will always attempt to imitate the provided state sequence, and the thing we are learning here is the inverse dynamics model, which dictates what will actually happen when we make that attempt. So for the sake of the presentation, I'm gonna talk about the deployment first. So now about the demonstration. So now I'm gonna first show the demonstration. Each task starts from a starting state S0, and here S0E shows the expert's starting state, E represents expert. So it starts from S0, goes to next state S1E, and next S2E, and so on. The agent has access to an inverse dynamics model, and it applies it on S0 and S1, and it infers the action that should be taken, and then executes that action and goes to the next state S1. And here S1 and S1E are different because the inverse dynamics model is not perfect. Then from S1, it again uses the inverse dynamics model on S1 and S2E and infers the next action, and then uses and executes that action and goes to the next state S2, and so on. So this was the deployment strategy. Now I'm gonna talk about the training strategy. So there are infinite number of inverse dynamics models, and each of these models result in a imitator trajectory, which are shown here with red. And so we are trying to find the trajectory that has the highest reward. So we are not trying to find the inverse dynamics model that leads to trajectories that best match the green trajectory, but rather inverse dynamics models that lead to high scoring trajectories when attempting to follow the green trajectory. Now the steps of training. We initialize an inverse dynamics model. Then we pre-train the inverse dynamics model by collecting data using an exploration policy. This exploration policy can be random or a pre-known policy. Then we use inverse dynamics model on the current state of the agent and next state of the expert to calculate the next action. Then we execute the action and collect the reward. And then we train the inverse dynamics model to maximize the reward and go back to step 3 to repeat the process. Now the experiments. We use 3 robot control domains to evaluate our algorithm. One is Mojoko simulator, one is SimSpark simulator, and the last one is UR5 arm robot. The hypothesis that we are testing is that RIDM is able to learn tasks efficiently with comparable performance compared to the demonstrator. And if the demonstrator is suboptimal, RIDM is potentially able to outperform the demonstrator. So in this presentation, I'm not going to talk about the experiments on Mojoko simulator, but I'm going to talk about the other 2. So the first set of experiments that I'm going to talk about is in the SimSpark simulator. This simulator is used in 3D Simulation RoboCup, which is a competition that is held every year. There are many teams participating each year. Each team has 11 players, like a regular soccer game, as it is shown in this video. Each of the players is simulated now. And all of the skills, such as walking and kicking of the players, should be developed by the teams. Developing these skills is challenging, and if a team has a better walk or kick, they would have the advantage over other teams. Also, at the end of the competition, all of the teams should release a binary of their teams, which could be used to play against them. The only information that could be accessed through that binary is the joint angles of the agents. In other words, their states. So the hypothesis that we want to test here is that whether we can learn other teams' skills and potentially outperform them using these binaries. The 2 tasks that we consider here are fast walk and long kick. And the demonstrations are from FUTK and FC Portugal. These 2 teams are 2 of the best teams in walking and kicking. So ideally, we would like the code, their code, the code that these teams use to generate their behaviors, but because we only have the binary, we only get the joint angles of agents running that code. And note that the reward functions for these 2 tasks are designed by ourselves based on how fast the walk is and how far the kick goes. And these reward functions are not necessarily the same as the ones that the demonstrators are optimized for. So the demonstrations are suboptimal with respect to the reward function designed by ourselves. So our experiments are on SimSpark 3D simulator show learned behavior outperforms the suboptimal experts. So the first experiment is for fast walk, and the demonstration is foot K. The learned behavior is shown at the top and the demonstration at the bottom. And we can see here that the learned behavior is very similar to the demonstration, but it's faster. The same thing happens for FC Portugal. Again, the learned behavior is at the top and the demonstration is at the bottom. Again, the learned behavior is very similar to the demonstration, but with a faster walk. So the interesting thing here is that for each of the demonstration, the learned behavior is very similar to that demonstration, but it's different between the different demonstrations. Even though that they are optimized for the same reward function. As you can see for FoodK, the steps are shorter, and for FC Portugal, the steps are longer. So they are attempting to follow the demonstration while they are maximizing the reward function. And now for kicking, it's again the same. First for FoodK, the learned behavior is at the top and the demonstration is at the bottom, and we can clearly see that the learned behavior, the learned kick, is goes much much longer than the demonstration. And for FC Portugal, it happens again. The same thing happens again. Now on UR5 arm robot experiments, our experiments on UR5 robots show learned behavior outperforms robots' default PID performance. One of the tasks that we considered was pushing task, and the demonstration is shown here. It's 10 times faster than the real video. We can see that the robot starts from a starting position and goes down and pushes a water bottle. Using the default UR5 PID controller, we can see that it fails to execute the task, and the water bottle falls down. But the learned behavior, we can see that it's very similar to the demonstration. The robot executes the task almost perfectly. Now, to summarize, we propose an algorithm to combine imitation learning from observation and reinforcement learning that requires only one state-only demonstration and can potentially outperform the suboptimal demonstrator. And at the end, I want to thank my collaborators, Brahma Pause, Josiah Hanna, Garrett Warner, and Peter Stone. And if you had any questions, please contact me with using the email provided here. Thank you.